All right. Um, simple harmonic motion and gravitation is Unit 7 of Physics C. Okay. Um, so, uh, this is this is like 15 sections in this unit. They go by really, really quickly though. Some of the sections, most of the sections, I think there's what a total of like 12-ish pages in this notes packet. Maybe a little bit more. 13 is 13 pages in this note packet. So each, on average, they're less than like a page, right? Okay. Review of simple harmonic motion. So first off, PM is periodic motion. SHM is simple harmonic motion, which, if I diagram correctly, illustrates the relationship. It's this right here. Okay, it's important to understand. I don't have a highlighter. Normally, I highlight this box and I fill it with a highlighter so that you know it's this one. But it's this one right here. Okay, it's very, very important to understand that periodic motion is a broad term for any motion that repeats itself over and over again. Simple harmonic motion does repeat itself over and over again, but there's actually some specific conditions for something to be considered simple harmonic. Okay, and I'm actually going to go over those conditions. I can't remember, just off the top of my head, I can't remember too well if you do it in Physics 1 or not, those conditions, but you're definitely going to need to know them for Physics C. And I'll show you some of those conditions and how they're kind of pretty easy. I'm given a position versus time graph, and I actually need to sketch the other 5 graphs, and it's the same time interval. I think there's actually a question on the website that's very, very similar to this. But I think in that one they actually give you values. Now, one thing to note is that in Physics 1, it was weird because we had to look at like the slope at each of these like kind of points and stuff to figure out what the velocity should be, right? You don't really need to do that though, because you're in Physics C now and you can do calculus. Um, you know, then you got to recognize that this is a sine curve. This is a sine wave, right? Well, if you differentiate, because you know the derivative of position is velocity, and the derivative of velocity is acceleration, right? If I dv, if I d over dt this, okay, then I end up getting a sine curve now, okay, and I hope I can draw it really pretty. Nope, I didn't draw it very pretty, but that's okay. And it should intersect with 0 right there. It probably isn't super, super clear. Okay, I end up getting now a cosine wave. Well, guess what? What do you think is going to happen if I d over dt this? Okay, if I differentiate it, I should end up getting a negative sine curve. So my acceleration is going to look almost, almost opposite. Actually, it's going to look opposite my position. Okay, can you see that? Probably not. But it's going to look kind of like this. I think I drew that pretty decently well, right? Okay. So yeah, you just gotta recognize, derivatives. That's the easiest way to do it. Okay. Any other way, uh, just be careful, right? And this gives me a negative sign. Okay. The energy, there's not really a trick to the energy. There is kind of a trick to it. Okay. Potential energy should actually increase the further you are from equilibrium. Because if you think of a spring mass oscillator, if you have like a spring is, at its default length or whatever, you put a mass on it and you stretch it, you're giving it a lot of elastic potential energy. So the potential energy should actually increase, or should be at a maximum when the position is at a maximum or a minimum. Okay, I guess technically like this is a maximum, this is a minimum, but when the magnitude of displacement is really high, potential energy should also be really high. Okay, so we should actually have maximums at this first time A, and then again at C, and then when there's no displacement from equilibrium, it shouldn't have any potential energy. So it should be 0 at the other timed segments. This is going to look kind of like this. Okay. It'll look kind of like that. That's actually probably the best I've drawn it, even as I lectured on it in my classes at school. Okay. The kinetic energy, okay, is going to be inverse of this because again, if you have an increase in potential energy, it needs to be complemented by a decrease in kinetic. So this is actually just going to be the inverse of everything that we've seen here. Okay, or we saw in the potential energy. So this should go. I'm not going to make the sound effects because it's going to get really annoying really fast, right? So it should look like pretty much the opposite, right? Okay. It should kind of complement each other. Again, when I'm talking about spring potential, when I'm talking about potential, I'm talking about like 1/2 kx squared. Well, as x increases, u should also increase as well. Okay. And then, of course, this is 1/2 mv squared. Okay. 1/2 mv squared. And so the less potential energy that I have, the more kinetic energy I should have, if that makes sense. Total energy, though, well, again, if I'm gaining potential energy, I better be losing the same amount of kinetic energy. So my potential energy, or my total energy, should actually just be a flat line across the board. Okay? There shouldn't be it should just be a flat line at a constant value because we're not losing any energy and we're not gaining any energy in the system. Okay, we don't have any unbalanced external forces that can do that for us. Okay, and the final point I want to make real quick is that when we talked about conservative and non-conservative forces, we said that if any one of the conditions was true, then all the conditions had to be true. It would imply all of them. And this is kind of the same thing, but also not really, because instead of it being one condition being true, it needs to be that a whole box needs to be true. So in order to prove that something is considered simple harmonic motion, you need to have one of these boxes be held true. And then that would confirm um, all the remaining boxes as well. So, for example, if you can confirm that force is directed opposite displacement, that's great, but you also have to confirm that force is linearly proportional to displacement. Okay? And so, if you go to like the third box or the fourth box, these only have one condition in them. So if you prove that one condition, then you prove all these other conditions too. Okay. Let me just remind you of a couple of really relevant simple harmonic motion equations that you should have learned in Physics 1. The first one is the spring force equation. Okay. It's negative. Okay. There's typically a negative there. That's because it's a restoring force. So it opposes what's being done to the spring. It opposes displacement. Okay. Another important one is that if you want to find the position of an object, you can do the amplitude, which is capital A, times the sine of the angular speed, omega, times time. Okay? Let's say that you have a spring mass oscillator. You use T sub s, which is period of a spring mass oscillator, and you get 2 pi root, okay, m over k. I'm actually going to show you that a little bit more in depth here in just a little bit, or in a later section, okay? If you have a pendulum, that's T sub p, okay, you can just use 2 pi root L over G, okay? So you hopefully should have learned last year that this is independent of the mass that you put on the pendulum. And the final point here that I want to make is the spring potential energy, which is U sub s equals 1/2 kx squared. Okay, these are just some important equations for you to know because they do pertain to simple harmonic motion, and we're going to use them quite a bit. Okay, that's section 1. Okay, we'll be back for section 2 here in a bit.